In this video, we're going to be looking at what's called the predator-prey system, and we're using differential equations to model this predator-prey system. Now, we've looked at situations that model the growth of single species that live independent in an environment. But a more realistic model is one that takes into account some interactions between the species. The model that we're going to be looking at involves two differential equations. First, let's consider a predator, which feeds on the species considered the prey. So for instance, we're going to use rabbits and wolves. But there are other models out there that you could apply this to. Our model will have two dependent variables, and both are functions of time. So we're going to let R of t be the number of prey, rabbits, and W of t is going to be the number of predators. That'll be our wolves. Now, in the absence of predators, the ample food supply would support exponential growth of the prey. So we could represent that growth as dr dt equals k times r. Now, in the absence of prey, we assume that a predator population would decline, because then we wouldn't have the food for the predator to feed off from, and so that population is going to decline. So we have dw dt, the rate of change of the wolves, equals negative r times w. If we have both species present, the main cause of death to the prey is being eaten by the predator, and in order for the predators to survive, they must eat the available prey, which is their food source. Now, the two species encounter each other at a rate that is proportional to both populations. The more rabbits and wolves we have, the more often that they're going to have these encounters. This is a system that incorporates both of these assumptions in our differential equations. Now look at the first differential equation, dr dt. We said without the predator, the rabbits would grow exponentially, which would be our k times r. But then when we have these interactions between the rabbits and the wolves, the rabbits are going to lose those interactions, so we're going to have to subtract off a portion of the rabbit population because of those encounters. And the second equation, dw dt, if we don't have any rabbits, the growth rate of the wolves is going to be negative, so it would be decreasing. But with the encounters between the rabbits and wolves, the wolves will now have a food source, so the population would tend to grow. These equations are known as the predator-prey equations, or the two mathematicians that came up with this model is Lotka-Volterra, so we call it the Lotka-Volterra equations. Now, a solution of this system has to be solved simultaneously. Let's look at an example. Suppose that the populations of rabbits and wolves are described by the Lotka-Volterra equations. So we're given our parameters, our k, a, r, and our b, and the time is measured in months. So we need to find the following. So first it says find the constant values, the equilibrium solutions, and interpret the answers. Equilibrium solution comes from when the growth rate is equivalent to 0. So we would need to set our dr dt and our dw dt equal to 0. And then we could solve to find the equilibrium. So this is just plugging in the given information to our equations. And now we're going to set those equal to 0 so we can find our equilibrium solutions. Now, top equation, we're going to factor out an r, So we would have r equals 0. We'd set r equal to 0, and the quantity 0.08 minus 0.001 w we would set equal to 0 and solve. In the bottom equation, we would do the same. We'd factor out a w, set w equal to 0, and then also set the other quantity equal to 0. And we would get r equals 0, w equals 0. Well, if we don't have a population of wolves and rabbits, the growth rate is going to be 0. And the other solution is w equals 80 and r equals 1,000. That's an equilibrium solution. Part B, use the system of differential equations to find an expression for dw dr. Now we can use the chain rule to eliminate t, but it does appear that we are just taking dw dt divided by dr dt. This will give us dw dr, the rate of change of wolves with respect to the rate of change of rabbits. Part C, draw a directional field for the resulting differential equations in the RW plane. Then use the directional field to sketch some solution curves. So here is our differential equation now, our dw dr. We're looking at the rate of change of wolves with respect to the rate of change of rabbits. Here is the directional field. We're going to choose an initial population, plot that point, and then we'll follow our tangent lines as we're moving from left to right. But in this particular example, it appears that we're going to have some sort of an oval or circular shape. Here are some solution curves to this differential equation. This is called the phase plane, and our curves are called the phase trajectories. Now the two different colors for each oval is the only reason that occurred was the computer program that I used to draw these curves. It required me to do two different curves, and it changed the colors. There's no reason for the different color in one of the ovals. Part D, at some point there are 1,000 rabbits and 40 wolves. Draw the corresponding solution curve and use it to describe both the changes in both population levels. Look at the graph and locate 0, 40. You can see that would be a point on this solution curve. Now let's look at what happens around this solution curve. We're going to start at 40 wolves, 1,000 rabbits. Now our equilibrium is 80 wolves, 1,000 rabbits. So there are not enough wolves at this point to maintain the rabbit population. So the rabbit population starts to grow. Now as the rabbit population starts to grow, the wolf population starts to grow. And this happens all the way up to about 2,880. Now we have an overabundance of rabbits, and the wolf population continues to grow. They have plenty to eat. As we're moving now around the curve in the red portion back towards the dependent axis, we see that the number of wolves increasing, but the number of rabbits now are decreasing. So at this point here, now we're moving in this direction around the curve. We can see that the number of rabbits now were here, but now they're starting to decrease. We're getting fewer as we move in this direction. Fewer rabbits. But the number of wolves are increasing all the way to this point up here. As we continue on around, we can see the rabbit population still is declining, but the wolf population now is starting to decline because there are so few rabbits. So this is the number of rabbits. Here are the number of wolves. We have an overabundance of wolves. So now all of these wolves don't have enough to eat, and the wolf population is starting to die off until we get to here. Continuing on around, the rabbit population now is starting to recover because the wolf population has declined so much. So the rabbit population continues to increase, and we're going to head around again, but the rabbit population is increasing, but now the wolf population is starting to increase also as we move around the curve. So we're just going to make this cycle of the populations increasing and decreasing. So here's our initial population, and we're moving in this direction. And then each one of these I have an explanation at each point. P sub 1, and we talked about those. Use part D to make sketches of R and W as functions of T. Now this is going to be something different. We are going to actually have two axes, two vertical axes, one with the rabbit population and one with the wolf population. Let's draw in the rabbit population first. So from our graph, we could choose different values of populations. We started out here at 1,000 rabbits, and as we moved around the curve, we increased to 2,800. Then we came back to under 500, and so on. So we could connect these points, and this would represent the population of the rabbits. We're going to do the same thing for the wolves. Now you will notice that when we create this other vertical axis, the labels as far as the numbers of wolves and rabbits don't match up, but we are going to create, when we had 1,000 rabbits, we had 40 wolves. So we have that axis on the right side of this graph, and this is just showing us the interaction between these two populations. And if we connected those points, it would look like this. And you could do the same exact analysis for this graph as we did with the previous directional field.